having a nice day, nice sunny day outside. Winter is somewhat returned. And anybody drive by a gas station or go into a gas station, see the sign saying this gasoline contains up to 10% ethanol? And think about, oh, that's an IUPAC name for an alcohol. Anybody look at a bottle of rubbing alcohol you probably have in your house and look at the label and it says isopropyl alcohol, which is an alcohol that's mixed in there? Remember, when you leave the classroom, organic chemistry is all around you. All right, a couple things. First of all, since I finished alcohols and thiols and phenols, on Monday I will go through the alcohols problem set. I highly recommend you do that. And the reason why, open this up for a second, is test number 2 is coming up. I know you're all feeling good about test number 1, but as I told you, test number 1 historically is the highest average. You guys did real good. Test number 2 historically is the lowest average. Now this summer it wasn't, so it doesn't have to be, but test number 2 averages, years ago I had one class that got a 68 average. After that I started brainwashing them to break carbon-carbon single bonds, no, they bring their average up, and I do that from the start now. And I've had groups as high as 90s, but historically the average is somewhere in the mid-low 80s. So prove me wrong, study hard, because there's more material. All right, if I remember correctly, I started talking about ethers yesterday. Ethers are a molecule functional group where you have an oxygen with 2 R groups. Remember, R means anything with carbon and hydrogen. And R and R prime is like a map, X and Y. They can be the same or they can be different. And as always, when you look at an organic molecule, you should look for what's different. And if you look at the molecule I have on the board there, I don't think I went through that much of the nomenclature for ethers yesterday. I have a small little gift for you, and that is nobody really uses, unless you're using it for a contract or a patent, IUPAC nomenclature for ethers. Everybody uses the common name. So I'm just going to have to learn the common names. And here, first of all, what functional group do you see? Oxygen, carbons, carbons, ether. And the next question is, what's the common name for that? And the common name would be, you use your organic chemistry hands, and you hold it over, and you look, what alpha group is that? Ethyl. Hopefully both of your hands are organic chemical hands, and what alpha group do you see there? Oh, it's your old friend, the methyl group. Since this is a common name, there's no rules, so it doesn't matter which one you put first or second. And you can just easily call it ethyl methyl or methyl ethyl. I'll do it this way because that's the first one. But if you have these reversed, put 2 alkyl groups and then add the word ether. And that's how you do common names. Oh, good news, I spent last evening mastering the editing software. So hopefully by Monday, the lectures will be online so you can see them somewhere. And somewhere will be on Blackboard, hopefully. But I'll also, don't tell anybody, oh, it's on videotape. But anyways, I'll also post it on YouTube. So you're on full access. And the question would be, what's the common name for that molecule? So I'll let you try it. Reminder, all of you have lab today. Don't forget to be on time. If you're more than 3 minutes late, I will not, 3 or 4 minutes late, I will not let you do the lab. There's a safety considerations I'll be discussing. Also, don't forget the lab today should have a long sleeve top or a lab coat. You notice I have one of my acid shirts on. We decided to make the outward default engine for these. All right, let's take a look at this. And the question is, what functional group do you see? That's the first thing you have to answer. Oxygen, carbons, carbons. They're different, and this is an ether. And then what's the common name? You look at each alkyl group, methyl, and propyl. And then add the word ether. And you could have also had N-propyl methyl, it doesn't matter which goes first because it's common names. Now, next slide, I'm turning the will this be on a test, and same thing with the ACS, off. Just real quick, this is the IUPAC rules for ethers. Any functional group in organic chemistry, IUPAC has rules for them. You don't have to copy this down or learn this, but you'll see why I didn't do something first. See a little squiggly red line? That's because I didn't do this. There we go. How do you do IUPAC? Name the smaller alkyl group of the ether as an alkoxy group. There are different types of substituents. I'm not teaching you all. OR is called alkoxy. This is called methoxy. And then you take the longest chain and name it as an alkane. So longest chain 3 would be propane. This is called methoxy. And it's on carbon 1, so that's 1-methoxypropane. Isn't it easier? Methyl and propyl ether. And that's why we use common names most of the time. And when you get the bigger ones, they get more interesting, which you will never see on the test. Well, let's do one more ether. Now, 2 types of nomenclature question. One is, here's the structure, draw the name, give the name, here's the name. Draw the structure. I'll do this one, and then I'll give you one to try your own, so you know I share. And how do you decode an organic chemical name? You start from the right. Ether. Oh, I know what that is. And one of the R groups is ethyl, the other is T-butyl. Doesn't matter which side you put either group. I'll do it this way. And we have a T-butyl ethyl ether. And that's how you do it. And if you notice the IUPAC, propane, and you have to know what an alkoxy group is, methoxy.
Does ether always go at the end?
Does it what?
Does ether always go at the end of the common name?
Yes. If it wasn't there, it's not an ether. I can't think of an exception. All right, let you try one. And why don't you draw the structure for diethyl ether? Remember, there's always 4 bonds to carbon. All right, looks like the last hydrogens are just going down. All right, let's take a look at this, how do you decode it. You start from this way, go to there. Ether, I know what that is. That's an oxygen with 2 R groups on it. What are 2 R groups? Well, ethyl, 2 carbons. Di means 2, so they're both ethyl. And we have diethyl ether, which is probably the most commonly used and famous of all the ethers. And one of the things about the smaller ethers like this is they have very low boiling points. Let's see if I can find that the boiling point of diethyl ethers. I know underneath, below the temperature of your body, I think I mentioned, but it's always good to mention it again, that Wikipedia is so heavily policed that just about everything with organic chemistry is true on Wikipedia. Let's see, boiling point of diethyl ether is 94.3 Fahrenheit, 34.6. So it's right below body temperature. Why do I know? 2-semester organic does a reaction where they have to heat up, boil ether solution. And the way we did it when I used to teach at Michigan State was you had them use their hands to heat it up. That's all the heat you needed. All right. Because they have a low boiling point, they have a very high vapor pressure. In other words, they give off a lot of vapor even at this temperature, room temperature right now, and they're extremely flammable. Ether makes gasoline look like water when you compare the 2 flammabilities. It's really flammable. When I was an undergrad, the organic chemistry lab I was in, we had a number of people, well, let's say their skills were questionable, and out of 17 weeks, we had 13 fires. And a number of them were ether. Diethyl ether is more dense than air, therefore the vapor stays right here. If I had a beaker of diethyl ether right here, after a couple of minutes, if I took a match and lit it, you'd see a wall of fire go that way. I actually saw that somebody stupid enough did that in the lab. I was an undergrad, and luckily nobody was ever severely injured. But one of the things you should always be asking yourself in my class is, why am I learning this stuff? And the obvious answer is someone told you have to take the class, you want to get a good grade. But the other answer is, why should you learn organic chemistry? Well, let's look at diethyl ether. Ethers, and this is the first one that they found, have been used as inhalation anesthetics. When your doctor wants to put you out, one of the ways they put you out is with inhaling something, and it knocks you out. Well, back about 1830s, they found this did a good job. And it was heavily used in this American Civil War by the doctors through the 1900s. One problem, any spark, any flame, anything, you have a fire. A, you killed the patient probably. B, your surgeon got badly burned and that's the end of his or her, and that was probably his career, and that was a problem. Well, organic chemists found if you replace in an ether some of the hydrogens or all of them with halogens, it's no longer flammable. An example would this be, let's see, this is called isoflurane. That's a trade name, not a common name. And notice it's methyl ethyl ether where you replace the hydrogens with fluorines and most of them in the chlorine. And true story, many years ago I had this operation I needed, and I had a great surgeon, really did a good job, and he never liked working in the morning, so his earliest operation he'd start is 1 o'clock. So I'm laying on a gurney outside the operating room. It's 1 o'clock, I could see it's 1:05, and finally the anesthesiologist came to me and said, we're running a little late. And I said, what's wrong? He says, can't you tell your surgeon's not here? By the way, he's always late. I said, how can I tell you? All wearing masks and, the caps. And he started saying, asked me, what do you do? I'm an organic chemist. Oh, I'm the anesthesiologist. He brought over a bottle of this and said, here's what you're going to use on you for inhalation. We'll also inject it. And I started explaining what the structure was to him. And he was interested. Finally says, oops, I got to go to work. And I said, why? Can't you tell your surgeon's here? And he was. By the way, I survived. And this is what they used on me. They knocked me out. And then they also had one, how they say count back from 100? That's the first thing that knocks you out. And that's an important use of ethers. Ethers are also very good inert solvents to run reactions in where you don't want to use water. And I did a lot of my research in graduate school using a special cyclic ether called tetrahydrofuran. Now, how do you make ethers? Well, the best way, and the only way, there are two ways, but this is the best way, that's the Williamson ether synthesis, named in honor of their English chemist, Williamson, who discovered this or invented it. Either way, one's a synonym of the other. And that is where you take, now this is a different functional group, which I really won't ask you to learn the name of. This is called an alkoxide. It's made from an alcohol where you have a carbon and an oxygen with a negative charge. All molecules in nature have a net zero charge, so you need a cation, and usually it's sodium. And then you react it with an alkyl halide, carbons with a halogen. Remember, halogens can be chlorine, bromine, or iodine. And what happens is, and you'll learn about this next week in lab, I'll talk about it, you'll have me on a test. The oxygen negative charge attacks the carbon. By the way, organic chemists are really violent. Instead of saying bondage, we say attack. And you can look it up in the literature, we use that terminology. Attacks the carbon with the halogen, kicks it out, forms a bond to that carbon, and you get salt also, which I have on the board. Now remember, my questions on my test, you've seen already, give the organic product or product, but sometimes it's good to know that's what you're forming. And now, if we look at this reaction, if I take this molecule, react with this molecule, what do you get? Well, first of all, you have to identify what are you starting with. Ooh, what's different? Oxygen with negative charge sodium cation, R group. This is an alkoxide. This is R. Carbon, hydrogen, carbon, hydrogen. Ooh, carbon with a halogen. This is an alkyl halide. And this is my R prime. What do I get? What's ever attached to the carbon here, R is still attached to it. And then which carbon of the R prime group has the halogen, the N one, And something I'll do is turn it around. The end one of 3 carbons would be written like this. And that's how you do it. And you don't have to put to get sodium iodine, because I'm just asking what's the organic product or product. And why don't you try this one? What would be the organic product or product? Did I make a mistake?
No, that on
Okay.
on the product in that example, you want us to keep a negative on the oxygen or not? What in the product side?
On the product side,
Yeah.
it's gone.
Oh,
Because this molecule has no net charge. What happens is this attacks this and kicks out X minus. So that's where, because if you look at this, it's really Na plus X minus. All salts are ionic bonds. So that's where negative charge comes out. And thank you for your question. All right, question would be, what's the organic product or products for the following? Once I get things posted on Blackboard and the other place, I'll send out an email to all of you letting you know about it. I get to be a bit slow now. Starting next Friday, I'll bring in, well, there's no class on Friday. I guess I won't do it. I was going to bring in 8x10 glossy pictures of myself signed, autographed, and they'll only be $39.99 plus shipping. Instead of the other one, maybe I'll get some money. 10 million people clicks. All right, looks like everybody's done. Let's take a look at this and how do you determine what's the product or products, organic product or products. You look at what's different. You've got 2 organic molecules. Oxygen gets my attention and sodium too, and this is an alkoxide. Good news, I won't be teaching the IUPAC rules for nomenclature that there are. Next, what's different here? A halogen, alkyl halide. Williamson ether synthesis, I'll make an ether plus a salt. What's my R group? Ethyl. Therefore, R ethyl, oxygen. What's my R prime? This right here. Notice it's 3 carbons. Where's the halogen? The center carbon. So the oxygen will be to 3 carbons, and the center carbon will be attached to the oxygen. There's another way you could draw this, which probably is easier for a lot of you. Here's my R prime, oxygen, R group. Either way, I've just made ethyl isopropyl or isopropyl ethyl ether. And that's the Williamson ether synthesis. Now, on test number 2, unlike test number 1, I will have up to 3 synthesis problems. Any more than that, that's cruel and unusual punishment, outlawed at least up to this date by the Supreme Court. And therefore, let's do a synthesis problem with this. And look out, I'm going Technicolor. Blue marker for this. So the question would be, on a test or in real life, give the starting materials of the following reaction to make that product. And what do? Well, you do what you already know how to do. You look at the organic molecule and say, what's different? Oxygen. And what do I have? An ether. Oh, and I also have sodium halide. How do I make an ether? What do I react? An alkoxide plus alkyl halide. I'll call this R, and if that's the case, this is R prime. And therefore, if that's true, my two compounds, R is methyl, R prime is ethyl, which the halogen will be bromine. And since it's only 2 carbons, I know it's going to be on the end one, and I'm done. But wait, you say, Dr. White, what if I do this? Call this R prime, and this R. Well, if I do that, R, 2 carbons, alkoxide, and then R prime, 1 carbon, and my halogen is bromine, and that's the other one. Which one is right? They both are. And in real life, when you're doing synthesis, making things in the real world, there may be more than one way to do it. Now, I'm probably one of the few people, the only people right now in this building would know, and this is beyond the level of even graduate course chemistry, which one of these is the better one, and the answer would be this one. Why do I know that? Because I know cost accounting and synthesis, and these are cheaper than these to purchase. How do I know? Because I use those. And therefore, that's the only reason. On a test, both are totally correct. Now, when I took organic chemistry, the instructor never put the question marks on the test. You had to know there were 2 things. My gift to you is on my test, I'll always put question marks. If there's more than one thing, you have to start with. And, whoa! Thank you, everybody. I didn't even have to say try it, you'll like it. You are all jumping in and doing that. Thank you. Does that feel good? All right, I'll give you 7.65 seconds. 1, 2, 3. Let's do 3 again. 4, 5, 6, 7.2.8. I'll go to 8. All right, let's take a look at this. How do you do that? Before I show you how to do this, I'd like you to think back to last November. If it was last November, you're sitting in this room, this happened to be in this room, and I happen to be standing up here, I happen to have this in front on the slide, I put this up and say, what's the starting materials? Would you even know what I'm talking about? Would you even know what to do? Think about how much you've learned in a short period of time. I hope you all think that feels good. All right, let's do this. What do we have? What's different? What are we trying to make? Oxygen. It's got carbons here, ether. And something inorganic, which is rare for Dr. White, sodium halide, the salt. How do you make an ether? Williamson ether synthesis. Alkoxide plus an alkyl halide. Now, what's R? This. And Dr. White cheated. I made R prime the same thing. R prime is this. Therefore, what do you start with? R is an ethyl group. So I have this alkoxide. What's R prime? It's an ethyl group. What's the halogen? Iodine. And that's how you do it. And that's how you make ethers. And it turns out ethers, like I said, are very useful. Got to be really careful around them because the smaller ones are flammable. Also, the smaller ones, if you let it sitting open, and once you open the container, if you don't use it, it forms what's called peroxides, which are explosive. One time in grad school, our boss, my advisor, told the people in our lab, you know, that's refrigerator we have for these chemicals needs to be cleaned out. And why don't you do that tomorrow, talking to all the group, not just me, in that lab. So I started cleaning it out, and I saw this bottle, and I knew it should have been liquid. It was diethyl ether. And I saw some solids in there, and I said, that's not right. So I called, before touching it, I called my professor, Dr. Roosh, over, and I said, doesn't look right. And he said, whoa, slowly close the refrigerator. I'll let me do it. And he called the bomb squad for the police department, and they evacuated our lab because that was full of peroxide. They came in, you know, like you see in movies with all the suits and the big thing, and put the bomb in. And I found out later they took it out to the field, out in the middle of nowhere, and from about 300 yards away with a high-powered rifle, shot it and it blew up. All right, it's new functional group time. We're moving along, getting a lot of good stuff. And this new functional group is called an epoxide. Moral of that story is, when you're doing or working with organic chemicals, keep your eyes open and always use your brain. All right, if I have a molecule like this, I'll write a simpler version where instead of on the carbons R groups, I'll just have hydrogen. You'll look at that and say, oh, this is sort of like an ether. Carbons, oxygen, carbon. But these carbons, the R groups, are connected together. And in first class, you think that's an ether, and the answer is no. This is called an epoxide. What you don't know, and I do, is when you have certain atoms in small rings, they're all unhappy because they're all tight together and constrained. They want to be relaxed. And it's called stericin, not stericin, it's called this crowding. And this wants to open up in the worst way. And it can, by breaking an oxygen carbon bond. Ethers don't do that. In an ether, that bond is very hard to break. You can, but it's really hard to break. Here, in oxides, it's different. Now, there's a whole thing about UCAP and nomenclature for epoxides. I'm not going to ask you to learn it. I'm going to really stick to this one epoxide. It has a common name, which you don't have to know, but I'll use it in class. And it's called ethylene oxide. And ethylene oxide is an important molecule that's used a lot in the United States I've used it both in the lab and in the plants, where I work with a company that made products using ethylene oxide. I'm trying to be good, not slip into slang, because if you work with ethylene oxide in the chemical industry, we call it EO, short for ethylene oxide. Nobody calls it even ethylene oxide, and that even is a common name. Interesting thing about ethylene oxide, it's a liquid at room temperature or low pressure, and if you get oxygen into it, it'll explode. And one company I worked at where we used ethylene oxide, and they had about 1 million pounds of ethylene oxide stored on the site. We had research on a production facility, a plant there. It was a couple miles northeast of Great America in Gurnee. And one Friday afternoon, a bunch of us are sitting around and somebody posed the question, if our ethylene oxide tanks blew up, would we take out Great America? And they're about 5-6 miles away. The consensus was, well, some people would get injured, but we wouldn't probably kill anybody. We'd all be dead instantly because EO is quite dangerous stuff. But when handled properly, it's safe. Now, when you work with ethylene oxide, do not write this reaction down. You don't want water around because water pops the bond here. And the word I was searching for earlier is constrained ring. It doesn't want to be all crunched together in a small little ring. And this bond pops, OH goes to the carbon, hydrogen goes there, and you get ethylene oxide. Ethylene glycol, not ethylene oxide. And you want to always have it dry. All right, turn the switch back on. If you take an alcohol and react it with 1 molecule or mole of ethylene oxide, what happens is you break that carbon-oxygen bond, the hydrogen goes to the oxygen, and this oxygen goes to the carbon there of ethylene oxide. And you make this new molecule, which is now an ether alcohol. Notice right here, carbons, oxygen, carbons, ether. Notice right here, carbon hydroxyl group, ether alcohol. And if we look at this following reaction, the question would be, what's the organic product or products are the following? What's here? Ooh, an alcohol. How do I know? Hydroxyl group on carbon. Here's my R group. Oh, 3-membered ring, 2 carbons, oxygen, ethylene oxide, epoxide. What do I get? Well, myself. I get this ether alcohol. What's R? 2 carbons. I have my oxygen, I have my next 2 carbons, and I have my hydroxyl group. And I form this molecule. Yes, there's an IUPAC name for that, but I'm not going to teach you or expect you to know how to do that, because it has more than one functional group. Now, one of the questions you should always ask yourself is, why are we learning that? Well, it turns out a number of the products where you're at, alcohols, certain alcohols with ethylene oxide, are found in your cosmetics, especially your skin creams and hair conditioners, and other things too. Running out of boardroom, this means this reacts with this to make something, and the question would be, what's the product or products you get? Looks like everybody's done. Let's take a look at this. What's different? Ooh, hydroxy group on a carbon, alcohol, ethylene oxide. What happens? You get an ether alcohol, H goes here, this oxygen goes to that carbon. And what's my R group and butyl group? 4 carbons. Therefore, what do I get? 4 carbons. Oxygen, 2 carbons. And then hydroxyl group. And here's the molecule you get. And this molecule, if you go to the supermarket or other place, big box store, and you get one brand of oven cleaner that's used for cold, not heated ovens, where you have to heat it up, you can just put it on there cold, let it sit and wipe it off. That's the key chemical that cleans the gunk out of your oven. Well, it's also used in another thing. I don't know how many of you remember back in 2010, probably one of the worst, if not the worst, environmental tragedies that happened on our planet was the Deepwater Horizon oil spill in the Gulf of Mexico. And that was an oil well that was a rig that was owned by Standard Oil and some other people, and they had it blew up. The safety devices that should have shut off the oil under the sea malfunctioned, and we were getting millions of gallons of oil pumped in. I forgot how many days and months it lasted, but all this oil into the sea there, into the Gulf of Mexico, was not a good thing. Quite bad thing, environmentally, both to the water, to the sea life, and turns out humans too. And one of the things Standard did and their contractor, they were pumping this dispersant into the water that's separated and supposed to disperse the oil so it wasn't hazardous. Well, wrong, that doesn't. But the product was called Corex oil dispersant. I think it was Corex 5942 or some number like that, don't quote me. And at the time, I was wondering, what the heck is that? And one of the things you don't know, I do, is any chemical sold in the United States, there is always a material safety data sheet for that. And if you go to your local favorite internet search engine and put in the name of the chemical and MSDS, they'll show you stuff. I think it was this one here, but I'm not positive. You'll see some MSDSs, and let's go to this one. I don't know if this is. And you'll see what's the composition, and this is not the right one. But anyways, when I did that, after I was saying the fact that over the period of time, they put into the Gulf of Mexico 1.84 million gallons, that's almost 10 million pounds of this Corex, and that's made up of 60% of this. So that's 6 million pounds was put into the Gulf of Mexico. When I looked up the MSDS sheet, because I was curious, I found out this is toxic to marine and human life. They're quite hazardous. Well, if you're putting in 6 million pounds into the Gulf of Mexico, that's not good. So being a responsible citizen, what I did was, first I tried to call the Coast Guard, who was in charge of that, and I got some idiot, and I'll leave it at that. And when I wasn't getting anywhere there, I figured, I gotta do something, so I called MSNBC. I also called the New York Times, and I also called a few other places, and let them know. And I'm sure I wasn't the only one. And soon, this got out into the news, and they finally had the governments finally, too long, weeks after that even, got them to stop doing that. And if you followed the workers who were cleaning up the beaches, they were coming down with some of the health problems from that dispersant. And the oil too. Sad story, but true. But these products can be used for good uses and not so good uses. You just have to look what's hazardous and what's not. How am I doing time-wise? What I'm going to write on the board, you don't have to write down, but it will illustrate an important point. If I take this molecule, react it with ethylene oxide, I'll get this ether alcohol. What's R? Methyl. If I take the molecule I just made, look at the end, I've got an alcohol. I can react it with another molecule of ethylene oxide. Again, don't write this down, you don't have to. And now this new R group will do the same thing. Here's my new R group, O, CH2, CH2, OH. And this new molecule, look, I have an alcohol there. I can react it with more ethylene oxide. And now, my new R group is that. And I get this. And I could continue reacting that. Again, don't. Now, if we look at this, when I add the first ethylene oxide, I put that on. When I add the second ethylene oxide, I put two of those together. And when I add the third one, notice I have three of them. How can I rewrite this? And notice I've added 3 molecules of ethylene oxide, and that leads us to Monday's reaction. When you have 2 or more molecules or moles of ethylene oxide, this is what you get of this form. And with that, I went a whole 7 seconds over, sorry. Those of you that laughed, please be on time. If you're late, I will not let you in. I'll let you in.